Fluid dynamics, the study of the flow of fluids. From sonic booms to von Karman vortex streets, our world is filled with natural phenomena that excite and perplex us. At Purdue University, mechanical engineering students receive a hands-on introduction to fluid dynamics through interacting with and manipulating these natural phenomena in the ME wind tunnel laboratory. During experiments in the wind tunnel, having a highly accurate probe positional system is essential for measuring non-uniform flows. Every individual millimeter contains a plethora of information on local pressure gradients, boundary layers, wake patterns, and more. Through the Purdue ME Summer Projects program, 2 new systems have been designed to improve the functionality and ergonomics of the wind tunnel probe positioning apparatus.
The wind tunnels in the Purdue ME laboratory use a potentiometer-based positional feedback system coupled with Lee screws and Thompson rods in order to move and monitor the position of the probe while taking measurements. The potentiometer-based system lacks necessary accuracy and repeatability as the integrated system is both inaccurate and susceptible to backlash. Furthermore, the process of removing and changing probes is lengthy and highly invasive. While the system's performance and characteristics are tolerable for their current application in ME309, expanded functionality and accuracy would allow for more in-depth research and educational activities.
The project requested 2 solutions for these problems, a retrofitted solution to optimize the existing system, and a replacement solution to create a better system from scratch. Design requirements include increasing the positional accuracy of the system, minimalizing backlash with improved encoder systems, integrating probe-sided feedback control via Arduinos, developing a probe quick change system, expanding the probe control to include Theta Control, and exclusively for the replacement design, also including Z-axis control.
For the X, Y, and Theta ranges of motion, all range and accuracy requirements were either met or exceeded. Quadrature encoders with resolutions of 40,000 points per revolution were utilized for all axes of movement to track and measure the position of the probe, which greatly improved the accuracy of probe positioning and feedback systems. The theta position encoder is directly driven by rotating a set of gears, while the X and Y encoders are driven by rotating lead screws. The thread pitch of the lead screw is used to create a linear motion reading relative to the rotation of the lead screws.
Most notable about this design is the inclusion of separate linear encoders. These new all encoders have an accuracy of plus or minus 10 micrometers, and they have 0 backlash because they are separate from the linear rods controlling the position. The Z-plate glides along rails affixed to the top plate, which allow it to make a smooth, consistent connection to the sealing felt underneath the test plate. The Theta Control apparatus consists of a gear that sits atop 2 pieces of Delrin that serve as a bearing. The slot in all 3 of these pieces can align to form the first half of the quick release bracket. As can be seen here, the entire probe apparatus can be removed with only the removal of 2 screws and the loosening of a couple set screws. This process is much less invasive than previously, as you don't even have to remove the top plate to switch out the probe. To incorporate probe-sided feedback control, we designed an Arduino-based system that will directly read and zero the encoder values, and then port that data to LabVIEW. As a proof of concept, this breadboard demonstrates the code using basic 2-channel quadricur encoders as inputs. Spinning the encoders increments the associated dimension, defined by a calibrated scaling factor for each degree of freedom within the code base. Turning the potentiometer, which is being used in place of a simple switch, changes the 2-line display to show either X and Y or Z and Theta dimensions. To zero the encoders, the user must hold down each dimension's associated zeroing control button for 3 solid seconds. The required delay, along with the audio-visual feedback, ensures that the probe won't be accidentally zeroed in the middle of an experiment. That concludes this presentation. Thank you for watching.